All right, so you're welcome. In this discussion, we're going to look at the histology of the skeleton, in short, bone tissue. Right? So bone tissue is a type of cartilage. So we said there are four basic type of tissues. Sorry, bone tissue is a type of connective tissue, right? So we say there are four basic tissues. That is muscle. We also have nervous tissue, we have epithelial as well as connective tissue. So bone tissue falls under connective tissue. Remember, there are broadly two types of connective tissue. What we call connective tissue proper, the actual tissue that enables attachment, support, and anchoring of various tissues to one another. And then we have connective tissue with special properties, such as cartilage, blood, and bone tissue. So this is an introduction to the skeletal system. So first of all, what is the function of the skeleton? So the skeleton is a supportive framework. Other than that, the skeleton is essential for mobility, or what you can call locomotion, because of what happens at the joints. So we call that as articulation, when joints are being kinetic, they are in motion. Then we have protection of internal organs. For example, we have various internal organs that are vital for life. Heart, lungs, and the great vessels, all those organs are protected by bony tissue. So you find that most of the organs, the soft organs and those that are vital, are closest to the bones, or they are protected by the bone. Example is the brain. Brain is enclosed by the hard bony structure, what you call the cranium or the vault. Then we also have hematopoiesis. So we have flat bones in the body, for example, the pelvic bones, the sternum, the long bones like the femur, the humerus, the ribs, those bones, the scapula, those bones are essential for production of blood cells. We see that before birth, the spleen performs that function because we don't have bones. Okay, when the fetus is forming, there's no bone, there is cartilage. Then that cartilage is transformed into bone. Then there's excess storage of excess calcium. So it acts at the storage site for calcium. So calcium we get from diet. Then after, we see that whatever the body can't use at that particular time is stored in bones, and bones become dense when they are calcified. Composition. So there's water, 25%. Then we have inorganic and organic elements. So organic elements, these are hydrocarbon elements. Okay. And then under that, we have the matrix, which is the product that is secreted by bone-forming cells. Then we have the bone cells themselves. All right. So we have cells that form bone and cells that maintain the bone. So we have osteoblasts, bone-forming cells, osteocytes. These cells maintain the bone. Then we have bone-degrading cells, known as osteoclasts, more like macrophages of the bone. Think of them like macrophages. Now, these, instead of engulfing foreign matter, they destroy the osteoid, which is secreted by the osteoblasts. Then we have inorganic constituents, which are now gotten from the diet that we ingest, for example, calcium phosphate and calcium carbonates. So these form 50% of the bone itself. Then the remainder is water and bone cells plus the product of those bone cells. So basically that's the composition. Types of bone. So basically there are two types. Okay, I'll be quick on this one. We have what we call compact bone or cortical bone. Then also have spongy bone or cancerous bone. What is the difference? So I'll go direct into that. So this one we're looking at is a combination of compact bone and spongy bone. So compact bone is hard bone. Sponge bone is soft bone. All right. Now, this is one bone gotten from a long bone. So looking at the shape here, this is the humerus, the bone of the arm, because of that depression there. Then that's a medullary canal. Long bones have a canal like that. Now, inside the canal, if you look carefully, you see that there are those honeycomb structures. So you see those spaces because there's a space there, space. That is spongy bone. Spongy bone has space or cavity. And that cavity is filled with bone marrow, red and yellow marrow. Red in young persons. Then as we age, that red marrow is converted to yellow marrow, which is fat, right? So most of us, we find that inside the bone there, instead of having red marrow, we have yellow as we age. So the functionality in terms of producing blood cells decreases. So what you have now is fat. So now we're going to look at compact bone and see how it is made. Then later on, we'll look at spongy bone. So the most important feature of compact bone are what we call Haversian systems, or what you can simply call an osteon. So think of them like bundles of sticks. Okay, if you have one stick, it's easy to break it. Okay, or you have one big stem, it's easy to break it. But if you get small sticks and then you make a bundle and then break that one, it's very difficult. So that's how bone is, a compact bone is made. It is made up of these cylindrical. They run throughout the length of the bone, so they'll be like that in its longest axis from top to down. But there are so many of them. So this is one Haversian system, or one osteon, another osteon, another osteon. So now let's look at the structures that makes up an osteon. So osteon has a central canal. That one there, that one, that one. Now this central canal is filled with blood vessels, lymphatics, and nerves. So there are blood vessels there, artery vein, lymphatics, and nerves. So bone tissue. So bone tissue is a living tissue. Most times we think of it like a dead tissue, but it's not. It's living like muscle and also undergoes injury and death also. So bone tissue can die and requires, regeneration, just like blood vessels, connective tissue, epithelial tissue, muscle, and nerve tissue. So that's why there are blood there. Vessels bringing blood and nutrients. And then we have lymphatics to drain any excess fluid, that is interstitial fluid. And then we have nerves for sensation. Bone is broken, there will be pain, because nerves that are there are also broken, what you call fracture. Now, around each central canal, that's the central canal, central canal, central canal, there are more like circular rings. So those are called lamella. Lamella. If it's plural, if it's one. If it's plural, you call them lamellae. You add E at the end. So one lamella, several lamellae. So they are circular. That's why they are called concentric lamellae. So the oldest lamella is at the periphery. Then was replaced by this one, replaced by that one. So this is the newest lamella, the one that is closest to the blood vessel. Now, this is the oldest one, so there are cells there, right? Now, since the oldest one is being pushed far away from the central canal, cells that are in the furthest lamellae need the nutrients, gases, and so on. So how do they acquire that? So you're going to find small channels, or what you can call rods, that these cells will use to get nutrients. So those small channels will have to link up with the central canal. So we call those as canaliculi. Okay, canaliculi. Now, these are essential because they enable these cells that is far away from the blood vessels to receive nutrients. So single is canaliculus, like you can see there. Then plural is canaliculi with I here instead of US. So there are several of them. Now, each canaliculi leads to a single cell. So there are multiple cells there. Each cell should have a canaliculi. That canaliculi goes all the way to the central canal. So nutrients, minerals and so on would diffuse from the central canal through the canaliculi and reach these cells. Okay. So that is important because these cells, if they don't have any nutrients, gases and minerals, the cells die. And that way bone tissue also dies. Okay. So these cells are fixed in this position. They're not mobile. So between each lamella, this is one lamella, you find these cells with their canaliculi. Now, those spaces between canaliculi where you're going to find cells is what we call lacuna. So that is lacuna. So first structure we talked about was central canal. Number 2 are lamellae. Number 3, canaliculi. Number 4 are lacuna. Now, lacuna is simply a space between lamellae. So this is new lamellae, older lamellae. This we can say oldest. Now you can see the gap there, and then you see a green stuff. That's a nucleus. And the yellow one is a cell. Now that space there is lacuna. So each lacuna is occupied by a single cell. One cell for each lacuna. One cell for each lacuna. So now this lacuna will have that canaliculi, which goes to the central canal. The nutrients will flow central canal through canaliculi to reach the lacuna where the bone-forming cells are. So these cells are osteocytes. These are osteocytes. You also find osteoblasts. Now, osteoblasts are much bigger than osteocytes. The function is more or less the same. Osteoblasts are immature and they are actively forming the bone. They are secreting the osteoid. Remember osteoid here. This is the matter that is secreted by bone-forming cells. When osteoid mix with inorganic constituents like calcium carbonate, calcium phosphate, the bone hardens. Now, when the cell is actively producing the osteoid, we call it osteoblast. When it stops producing that, it is now called osteocyte. So to make things simple, osteoblast is immature and actively producing osteoid, whereas osteocyte is mature and inactive. So an osteoblast turns into an osteocyte and remains dormant in that bone. So that's why osteoblasts are called bone-forming cells, whereas osteocytes are bone-maintaining cells. For the bone to remain the way it is, it's because of the presence of osteocytes. When the bone is fractured, to repair that bone, we need osteoblasts. Once the reparation has occurred, those osteoblasts turn into osteocytes and remain inactive. So that is the structure of a single osteome or Haversian system. So again, roughly is central canal with several concentric lamellae. Then we have canaliculi connecting the central canal to each lacuna. That's a lacuna. Then in each lacuna, we find mature osteoblasts. We call those as osteocytes. So those are osteocytes. The bone maintaining cells. So basically, that's a basic structure of compact bone. And you should be able to label all these structures without fail. Okay. There is another classification of bones. So bones can be classified based on length, based on shape, and also based on histological feature. The one we have done, this one is based on histology. What you see under a microscope, you see Haversian system, so it's a compact bone. So based on histology, or what you see under a microscope, bones are two types, or classified into two: compact bone and sponge bone. So this is compact. Let me quickly look at sponge bone. Yeah, this is spongy bone or cancerous bone or trabecular bone, if you like. Now, difference is that instead of having a Haversian system, sponge bone has trabecular. You see those spaces? Okay, that's a space. The one that is darker is a space. Then the one that is pinkish, that is a trabecular. So it looks like the honeycomb, the structure that bees make, where we get honey from. That's how a spongy bone looks like. And that's where it gets the name from, a sponge. A sponge is a kitchen utensil for washing plates and so on. So that thing can soak up water and so on, because it has spaces where water molecules can go. Same thing with sponge bone. There's a space there, space, space, space. Then with little physical structure, which is known as trabecular. So all this whitish part is trabecular. Now, these spongy spaces are essential because that's where bone marrow fits or accumulates. So bone marrow, like we were saying, is two types, red and yellow. In young bones, it is red marrow, which will occupy this space, that space, that space, that space. As we grow older, a red marrow is replaced with yellow marrow, which is fat. It's just replaced with fat. So nothing much about sponge bone. It's just trabecular with spaces. So this bone easily breaks as compared to spongy, to compact or cortical bone. Now, other classification, for example, is based on length. So we have long bones. Now, long bones have the following features: a diaphysis, which is this part, the middle part, then two epiphyses, these dilated parts at the distal ends and the proximal end. So this part is wide, that part is wide, then the middle part is narrow. The two ends are epiphyses, single epiphysis, epiphysis. Then the middle part is shaft or diaphysis. So all long bones have this arrangement. Whether they are found in the fingers, bones that make up the fingers are long bones. They have the similar shape. Bone making up the leg, the thigh, the arm, the hand, all those are long bones because of these three features that they have. In addition, long bones have a cavity inside, called that as medullary canal, where bone marrow is found, medullary canal. That being said, long bones, the outer covering is compact, very strong. Then the inner part is sponge bone, very soft. So long bones have two types of bone in it: a softer part, which is inside, and the hard part, which occupies the outer layer. So they don't easily break. And you see, long bones enable us to stand upright, together with the irregular bones of the spine. Then also are essential for mobility. Other bones are short bones, like in the wrist, in the ankles. Flat bones. These bones are flattened, like ribs, shoulder or scapula, if you like, hip bones, and bones of the cranium, the skull. Those are flat bones. So this is classification of bones based on shape. Flat bone, others are long, others are short. Then we have those that cannot have a definite shape, so we call them irregular. Facial bones, bones in the face, you can't define the shape. Vertebral bones, the shape is distorted, so you can't define it, so they're just irregular. Then we also have sesamoid bone. Now, sesamoid bone are bones that form within a tendon. So as the tendon is developing with age, these bones, or the tendon is converted into a bone. So we call those bones as sesamoid bone. The largest sesamoid bone is a patella. So patella is not present when we are born. It develops around second year of life. That ligament there in the knee, or tendon, that tendon in the knee is converted into a bone with age. We also have several other sesamoid bone in the palms and in the soles of our feet, but they are very small. They cannot be seen under a microscope. You can't even feel it. We are not even aware that they are there, but there are several of them. It's only that the patella is the largest and easily seen. So that is the other classification of bone. Okay. So like you can see, this is a vertebrae bone that is cut. The shape, you can't say whether it is rectangular, circular, it's impossible. So just call them irregular. But this one is flat. It's easier to say this is a flat bone. Okay, so we talked about this. Now let's look at cells that make up bones. So we have osteoblasts. I already explained. Osteoblasts are bone-forming cells. And then when they stop forming the bone, they are converted into mature cells called osteocytes, which become inactive. Now, where do these cells come from? So osteoblasts come from connective tissue. Now, when we're doing basic tissues, we say the most abundant cells found in connective tissue are what we call fibroblasts, right? This is connective tissue proper. Now, the same cells will be given a different name depending on the type of connective tissue you're looking at. So, if you're looking at cartilage, fibroblasts are known as chondroblasts. If you are looking at bone, fibroblasts are known as osteoblasts. So it's the same cell, except we are changing the name because it is a different structure. If it's loose, dense connective tissue, you are going to call it fibroblast. We can't call it chondroblast in loose or dense connective tissue. No. Now, osteoblasts are simply chondroblasts, right? Bones, especially long bones, develop from cartilage. So a fetus there doesn't have bones. A fetus has cartilage. They are very flexible. They don't easily break. Okay. So now those cartilage will be converted into bone, and therefore you can't call them chondroblasts or chondrocyte. If you hear chondro, it means cartilage. Osteo is bone. So it's just we're just playing around with the name. Now, what happens to chondroblasts for them to turn into osteoblasts so that they now form something that is hard instead of remaining as a cartilage, something that is very flexible? So transformation of chondroblasts into osteoblasts depends on oxygen supply. So when oxygen supply is low, chondroblasts are transformed into osteoblasts. They become bone-forming cells. If oxygen supply remains high, those cells cannot be transformed into osteoblasts. They will remain chondroblasts. That's all. That's the main reason why bone will be converted, cartilage will be converted into bone. It's just amount of oxygen. So the body knows how to play around with oxygen supply to the cartilage that the baby is born with. So towards 9 months, as human being is about to be born, that's about roughly 8 months. Yeah, 8 months of gestation. Chondro cartilage that is going to form the skeleton begins to be converted into bone. So the moment chondroblast turn into osteoblast, bone formation has begun. Okay, now that point where one or more chondroblast has been converted into osteoblast, we call that as the germinal center. Okay, now the long bones have one germinal center. You see them around, like I was saying, around 8 months, right? Now, what happens to the bone? So, number one is blockage in the blood supply. Okay, so germinal center or ossification center is the same thing. So the primary ossification center appear in long bones around 8 weeks. I was saying 8 months, sorry, 8 weeks. 8 weeks, you need to correct that one, 8 weeks. So what happens to the bone is the outer covering of the cartilage blocks blood supply to the cartilage. So when blood supply to the cartilage is blocked, cells in the mid part of the cartilage, I'll use this diagram for easier explanation because you can see and follow easily than reading those words. This is cartilage, still cartilage, still cartilage. Now, see that cartilage is whitish, but bone is going to have this different shade. So this is in a fetus. Now, around 8 weeks, this is what happens there. You see that collar. There's a brownish covering around the cartilage. So this cartilage has no collar. It has no outer covering. So cells in this cartilage, the chondroblasts, are receiving adequate amount of oxygen, right, from the surrounding blood vessels. So diffusion, gases, nutrients is easy. Now, around 8 weeks, you know, nature, or you can say God, what happens is this structure develops around the diaphysis of this cartilage. And therefore, cells inside there receive less and less amount of oxygen. Look at what is happening. The collar thickens, keeps on getting thicker, and therefore diffusion can't occur. Gases, nutrients can't penetrate through this layer to reach the cells inside there. What happens? These cells undergo some death, right? Because they're receiving less amount of oxygen. Then blood vessels enter now. Because those cells are dying, blood cells penetrate through the collar and enter the cartilage. The moment this occurs, bone has already begun to form. All right, so these blood vessels will bring now fibroblasts. But fibroblasts are the ones nala push no push. Easy. Atishine kwa chashe, tuko chiro kwa chashe na. Maybe to shimie. Stararego. Okay, so to be continued, okay? It's okay. I think I appreciate him. Natural but still record actually. So my students I record per Zoom. So hapa no chat na mute. I record per Zoom then